Hi, I'm Alex Thomas. I'm the principal data scientist here at Wisecube. And today we're going to be talking about detecting hallucinations and the measurement systems that we can use to do that. Uh, so, okay, so a little bit about us. I'm the principal data scientist at Wisecube, and we've been working together for a few years. And we've worked on various different technologies in different domains. Today I'm going to be talking about an issue with AI, but with specifically like how do we actually detect this issue and how do we know that we're detecting it correctly? So LLMs have been this really big improvement in processing natural language and have allowed people to do like a lot of really cool things. But there's a problem that they can have. They can hallucinate. So in this case, what we mean by hallucinate is that it's basically making up stuff. We'll talk more in detail about what that is, and that can lead to spreading false information, giving people the wrong information or bad advice. It can decrease the customer's trust in your system and hurt your brand name. And the LLMs also have like inherent bias. Also, there's a concept where it's called framing, where the user can accidentally uh, make the LLM give them the wrong result by framing a question a particular way. So these are all problems that can cause the LLM application that you're building to produce bad or harmful results. And some of these mishaps have been, expensive or very embarrassing. So, for example, and the Air Canada example here, their chatbot invented a policy, a refund policy, and they were forced to honor that. And then, of course, we have a bunch of other examples here, and likely we'll see more examples in the news. So these hallucinations are different than sort of other generation problems in the past. Before the rise of LLMs, language generation problems were usually around disfluency, so it producing sort of bad quality text. These ones, they not only are fluent language that's producing, but also to someone who's not an expert in the matter or who otherwise would not be able to know better, it looks reasonable, a lot of these outputs. And we can have like, serious brand damage and legal concerns. So how do we measure this problem? So first, I need to establish some terminology because we're going to be talking about measuring applications, and then we're going to talk about measuring those measurement systems. So that can get a bit confusing. So when I refer to the application, I'm referring to an LLM-based application. So a chatbot, a summarization system, etc. And when I talk about the measurement system, I'm talking about some sort of system for measuring such an application. So let's break down this thing into different tasks that the LLM applications can be doing. This is sort of a generalization. There's probably like more ways you could configure this and other things you consider, but these are sort of cardinal classical examples. So, for example, we start with zero context. That's just the very basic chatbot experience where just the person's giving some sort of small input. Oftentimes we think of it as a question, but some sort of small input into an LLM, and it gets usually a small output back, but it could be variable size depending on what it is. And there's no external information. Then there's a what we're calling a RAG Q&A system. So this is a question answering, but where there's going to be some context provided. So RAG stands for Retrieval Augmented Generation, and that's where we use the user input to retrieve relevant text, documents, perhaps just passages, and that's passed in with the question to the LLM to produce the answer. So this is going to be a more complex, but the idea is to make it more grounded, to reduce the amount of hallucinations from sort of the zero context Q&A. Then we have summarization, which is kind of a different task. In this case, there's not really like a question or a user input. We'll talk about how you can like optionally use that for some things, but in this case, there's going to be a large input and generally a smaller output. And this is has a much more complex concept of accuracy. So let's look into some of these use cases. So in the zero context Q&A, here we have like example of a question and answer. It's difficult to measure the hallucination at times because you need to find some sort of external data source to check the accuracy, factuality, what have you. And this is, as I was saying before, it's very susceptible to this notion of user framing. A lot of the newer LLM models, they've actually begun to train specifically to combat this, so that if someone asks a question that is like, why is South Carolina barbecue worse than Texas barbecue? Like that frames it as if that is the case. And so the LLM might be inclined to give an agreeable answer, to give an answer that does assert that the South Carolina barbecue is worse than Texas barbecue. So in order to measure something like zero context Q&A, you need to find an external data set. This can be done in a couple different ways. You can find some sort of external structured data set, and then you will try and match up things in the answer to the structured data. Or you can essentially back engineer it into like a RAG situation where you look for relevant documents and then you measure how well the answers match those documents. But it's one of the more difficult ones. RAG Q&A. So this is a very popular use case for LLM applications. But now we have three different sources of factual errors. You have LLM hallucination. So the LLM just making up something that's not true. But then you also have errors in the retrieved data that the LLM faithfully used. And similarly, incorrect retrieved data. So perhaps someone's asking like, what is a bank? And they're intending to ask the geographical term. So it was like the bank of a river. But when they ask that question, it gets a bunch of documents about the financial institution bank, in which case then the answer is incorrect. It's factually incorrect for the geographical concept of bank. But the problem was incorrectly retrieved information. So in this case, detecting hallucinations is probably better to look for consistency with the retrieved data. Because if we remember back to our how RAG-QA works, you get the question, you have a retrieval system that gets the contexts, then the LLM generates it. And so if you want to look for problems with your LLM, you should focus on what happens after that step. So making sure that the answer is correct for the data retrieved. And then the third scenario, which is summarization. Again, this is a larger one, and considering that this is taking in some data and then attempting to reduce it in a sense in making the summary. This can be difficult to measure in a different way than the ones before. You also have a problem here where so the user may provide something that is known to be factually wrong, but they want to summarize it. So, for example, perhaps someone is analyzing news articles containing misinformation, and so they submit such an article. If you are wanting to like measure the quality of the summarization in this task, you wouldn't want it to flag factually wrong things coming from the article, because that's something that the user is actually interested in capturing. So you would want to make sure that the summarization is being faithful to the references given. So this is an example where we can actually use something to focus it, where you can use a question to focus the evaluation. So this would be, as an example given there, we have some sort of patient documents and we want to analyze hallucination, but we're really concerned about what the summarization is saying about the drugs and the prescriptions. So we include in, depending on what your strategy is, and I'll go to the concept of strategy soon, we will include a question in that to say, oh, here's a question for the summary. And that can be used to focus the evaluation on that topic. Excuse me. So, we have these different use cases, and now we want to establish benchmarks and metrics for measuring these applications. Well, this is still a new domain. It's not like the NLP, natural language processing benchmarks of the past. We don't have decades of experience and research articles that we and data sets that we can use to do this. There's no even generally accepted metrics. There's no convention on like, oh, this is the metric you use to measure summarization. There are such metrics for pre-LLM measurement, but they don't really make sense in the like modern summarization, because so many of those metrics are also trying to capture this idea of fluency, which LLMs are doing such a great job at. There's really no point in capturing that. You want to capture the factual accuracy. And if this is the case for the measuring of applications, you can imagine how much less there is convention around measuring the measurement systems themselves. So let's talk about the measurement strategies and the models that we're going to be using here. So we've done a few experiments where we've taken some different strategies, including one we've made, and a couple different models. And we're going to show how you can compare these to find which measurement system is best for which situation. So the Pythia strategy, so this is one we have. This is one based off extracting claims in the form of triples, explained here, and then evaluating those. So the idea behind this is that if you are just sort of giving your inputs and outputs, just the text, to be evaluated by an LLM again, that you get less actionable information. By getting these triples that are then labeled as incorrect or correct, you can look to see what sort of hallucinations there are. If you are worried about your model and you have a domain-specific problem, this could point out that maybe you did not do sufficient fine-tuning in that domain. If your errors are if the claims that are being extracted that are wrong are the domain-specific ones. And so what you do is you extract these claims in the form of these triples. Here's an example with a 50-year-old man with a history of hypertension, atrial fibrillation, who is on Coumadin and Nidam, which is an abbreviation essentially means diabetes. So we have an example of like two triples extracted from that. The patient has diagnosis type 2 diabetes, and implied by that sentence, Coumadin treats atrial fibrillation. So once we have these claims, we want to classify them. We want to categorize them. So the idea is that we have the reference, which is, we are going to assign a certain level of confidence that that's correct. And we have the response. That's a summary that we're generating, or an answer that we're generating. And so entailment is claims that we can match between them and they agree with each other. Contradictions are claims that we can match on what they're talking about between the response and reference, but they contradict each other. Missing are the things that were not in the output, but were in the reference or the context. And neutral are things that are in the generated response, but not the original reference. Hallucinations are going to be in the contradiction and neutral category. The contradiction, obviously, those are harmful to the quality of your system, but neutrals are not necessarily harmful. It could be that there's some correct, there's some factual sentences that will be generated by the LLM in your application that are they're hallucinations in the sense that they're not from the reference, but they still might be correct. So those are a little harder to measure. So our metric right now focuses on entailment and contradiction, and optionally, this notion of reliability. So what we do is we essentially do a harmonic mean of the entailment and the non-contradiction. So that is, we do 1 minus the rate of contradiction. And reliability, if it's included, is going to be basically we're going to take those neutrals and try and verify them. And there's different ways you can like modify this metric, but this is what we use when we are producing an evaluation of a generated response. Another one that we're going to be comparing to is the grading strategy. So this is where we just have a prompt that's asking to grade the response with an A through F grade. So right now we're ignoring A plus, B minus, the pluses and minuses. And then we map it using sort of a common scale in order to get a score. So this is a simplistic one that we want to compare to the value of extraction. And then we're also going to be looking at a popular project out there, or a newer project out there called Lynx. And they have a similar sort of like a simple prompt, but instead of giving a grade, they give just a pass fail. And sort of like this notion of the granularity of the label or the prediction is actually be important. They also use the term faithfulness. They specifically exclude the question from being included in there, which is would hopefully like minimize the effect of any sort of priming done by the question. And it's built around their data set, which is a data set we use later on here, that has a binary label. So the models we look at are GPT-4o and Llama 3.1, 70 billion. There are other models we're looking at right now. Here's a list of some of them. But this presentation is just focusing on those two models at the top there. So now that we've talked about how we detect the hallucinations, we need to talk about how do we measure that detection. So this is sort of like this meta step where we are looking to measure the measurement system. Measure the measurement system. So again, talking about comparing that to old NLP benchmarking. There were like pros and cons of how benchmarking is used. There's a lot of data sets out there that are made well, some of them. They're specialized by tasks, so named entity recognition, sentence segmentation, cross resolution, different data sets for those. Sometimes they're from the same text, but they've been annotated for these particular tasks. And then there's also data sets specialized by domain, so medical, clinical, financial. And for these different tasks, there's known metrics that and conventions on them. The downside is that because of these data sets being specialized and some of them not being specialized, if you have a different domain than what's available for the task you're looking to measure, so if you can't find a data set for your task and domain, you're not going to be really sure whether the measurement of your system is accurate. So if the idea is like, I have a sort of a data set that's on social media posts, but my text is on academic articles. And so that's what the NLP system I'm building is for academic articles. Looking at how I perform on this generic social media set does not really give me reliable information for how I'm going to perform on the scientific articles. Also, some of the data sets are really old, as in like from the 70s or 80s, and most are very clean. So the sense that like there's been a lot of like pre-processing of the data. One of the worst things, that as far as for like trying to test out against natural data is some of these data sets come like pre-tokenized, where there's like extra spaces added in to make tokenization easier. So when we measure the measurement systems with the new LLM ones, we didn't need to do that with the older NLP processes because there were these conventions. So like the ways we had to measure it, they were known, trusted, established academically. And the tasks that we were doing were much more clearly defined. You can very clearly define what named entity recognition is. You're saying, oh, find me all the phrases that represent the entities of this type. Or co-reference resolution is something that is a little more complicated to actually define, but is clearly definable linguistically. When we're measuring the LLM responses, we're talking about factuality, consistency, faithfulness. These are much murkier concepts. So benchmarking is a very different thing in this sort of new LLM world than it was back in the old NLP world. Also, when measuring your measurement system, there's some special requirements you have. You need to have all the inputs, outputs of the systems. Generally, that's not a problem, but like there are some out there where they'll have like features instead of like the actual text. Preferably raw, none of those pre-tokenized ones. You also need good and bad examples. This is where it's like hard a lot of times to find a good data set where they'll just have sort of like, oh, this is because we're talking about generating outputs. So they'll just have like, what is the correct answer to the question and answer for a question and answer application? So like, for example, the BioAsk data set has a bunch of like really great questions in the biomedical domain and the ideal answers for them. They don't have the wrong answers for them. So we can't really use it to measure a measurement system. And also, you very much want to prefer to have human-generated labels. Because if you have like some sort of system generating the labels for you, then the question is like, well, okay, now how do we know that system is accurate? And you start getting like, oh, well, now how do we measure the labels that are used to measure the system that measures that? And it gets too deep at that point, then we have a Stack Overflow. So there aren't that many data sets that fit this bill, but more are being built because this problem is starting to be recognized, and there's likely legislation on the way. So the need for these data sets is strong. So let's go to the data sets that we're going to be using in this talk real quick. So we have the summarization data set. So there's the two CAGS sub data sets. One is generated from CNN and Daily Mail news articles. And they've been labeled by Mechanical Turkers. And then there's another one from BBC articles. The summary generation is done in like slightly different ways between these. So the good and bad examples that we have, or rather, we have like one example per article, and then we have the grades done by the Mechanical Turk labelers. Then we have the SumML data set, which is itself also generated from the CNN Daily Mail data set. But the summaries are generated in various different ways. And the labels are done by both experts and Mechanical Turks. So for the CAGS labeling, each labeler will label each sentence as a yes or no, as in like, oh, is this a good sentence in the summary? Is this accurate for summarization or no? And then what we do is we take a micro average across the whole response. For some eval labeling, there's the expert and MTurk labelers. Those are recorded separately in the data set, so we can distinguish them. There's actually 4 things that they measure: consistency, coherence, fluency, and relevance. We're just using consistency here. We found that there's actually not a lot of correlation between the experts and the Mechanical Turkers. So we actually just go with the experts. So we got these 3 data sets from a leaderboard for the Alliance Score project. And they use Spearman correlation with the human labels of these data sets to make their leaderboard. There's a problem with Spearman correlation, though, is that these 3 data sets have very low granularity in their labels. So in Spearman correlation, if there's a tie, so let's say, for example, items 10, 11, and 12 are tied, they'll all be given rank 11. There's a couple of other tie-breaking conventions out there, but this is a pretty common one. And what that means is if you have a system that's more granular, when you are looking at the when you're looking at the correlation of your data, you will get penalized for being more granular. So that's for not having the ties, especially when the ties are very extreme. So with this one, links, for example, just to explain why that was there, it doesn't actually support summarization. It just supports RAG Q&A. But with this metric, it looks like Pythia's doing very well for XSum, but the grading, the simple grading prompt is doing the best for the others. So when we look at the distribution of the labels, we notice that, like, okay, there's some granularity for the CAG CNN Daily Mail, but for XSum, there's basically just 4 values, and for the label histogram, there's fewer. There's like I believe it's like 12 values, and overwhelmingly they're all in that higher category. And what that means is there's a huge number of ties, like 80-90% of the data is tied. So the measurement of a very granular data set, like or a more granular data set, like what Pythia produces from this the accuracy metric I talked about before, is going to be like severely penalized compared to something that's much less granular, like the grading. So let's pick a different metric. Let's see if we can get a metric that's better for both. So let's look at mean absolute error. And this is the reason why this one's better for both. Is that what we're going to do is we're just going to treat the human labels as just like a line, and then we're going to measure the error from that line. That doesn't excessively penalize more or less granular systems. So in this case, lower is better. And it looks like now the Pythia system we have, which was, from our like previous work with other projects, should be very good for summarization. Oh, look, now it's doing much better. Now, of course, this metric works here, but it's not necessarily going to work for every use case. So let's talk about our RAG Q&A data set. So this is a data set that the Links project uses. It's composed of these other data sets, and all the labels are just pass-fail, which their system also is built to produce just a pass-fail. So when we measure this one with mean absolute error, it looks like Links is doing pretty well, but it doesn't really make sense in the binary one, because if we are comparing 2 binary variables, the error is going to basically just be like the based on the few that it disagrees on. So that's sort of a weird way of measuring that. And then the ones with more granularity are still going to be kind of penalized, because their values are all going to be kind of more in the middle, and then you're going to have the labels be this like extreme 0 to 1. So mean absolute error is not the right one, right? Not the right metric for this. But we can treat this as a binary classification problem, in the sense of we can try and figure out for these scores how well they separate out the passes and the fails. So let's look at some ROC curves and precision recall curves for Pythia. So we see varying qualities of performance across the different component data sets. And like this is very informative for classification, but again, it doesn't really work on the grading or link strategies because they're such granular metrics. So we need to find something that works for all of those. And so that means we need to go with accuracy. This happens to be the one that the Links project uses. But in order to use this one, we have to threshold Pythia and the grading strategy. The Links prompt works best overall for this data set. The claim-based Pythia strategy does better on summaries, but the idea is that the simple prompt-based ones do better on the RAG Q&A. So there's a couple different hypotheses. One is possibly in the Q&A, there's actually not enough text to extract a lot of useful claims. Another one, which is not listed here, is when we threshold the output of Pythia, we are sort of doing it in a very sort of numb way. And we're not taking into account the data. We just like pick a good threshold. Maybe you could tune it a little bit for performance. But for example, here I just picked 0.9 as a threshold, with the idea being that you probably want something that has a small number of contradictions, and so that's a good threshold. But with both the grading and especially with the links strategies with their prompts, they push that thresholding effectively off to the LLM. So instead of having to pick like one threshold for everything, they're asking the LLM to make that choice about like where it sits. So that allows the LLM to take into account the data when deciding whether it's pass or fail. So the conclusions for this one. Unlike with previous generations of NLP, simply just running a benchmark, oh, I'll go get a data set and run it, and now I know how my system's doing. That's not sufficient. You need a more sophisticated measurement system, and you need to understand how to use that system. And you also need to understand the data and the metrics you're using, understanding how close is the data to what you expect, both in terms of input data and output data. So, for example, if you have one of these data sets out there and it's measuring a bunch of like generated summaries that are generated in a way that's completely different to how your system generates summaries, they're not really going to tell you as much information. You also need to understand the metrics and how they work, and how for different data sets and different tasks, you might need different metrics. And then finally, measuring an application is an ongoing process, and you need to tune your measurement system. And this field is developing, so there's the tuning of the measurement system, which will always sort of be the case. But there's also, you want it to like keep up to date with like what the current measurement is as this field develops. So here's some future items that we're looking towards doing. There's testing against more strategies. We have a new version of the Pythia strategy in the works. There's also Ragas out there, which is another sort of extraction-based one, but it's not based off of like triples. It's based off of statements. And then if we want to test more models, we want to test large models versus small models. So like, for example, GPT 4.0 versus 4.0 mini, the 70 billion Llama and Link 70 billion versus the 8 billion. We want to see how those work. And then also working on compare like general versus fine-tuned. So like seeing Llama versus the Lynx model, which is based off of Llama. What sort of gains do we see from that? And also, we want to try calibration. So this is I think a very promising concept in this idea of measurement and improving the outputs of LLMs. And with that calibration, we can try different ensembling methods. But yeah, more on that in future talks. So now we'd like to turn it over to you and what questions you have. Thank you. Oh, so how do we compare different systems on our own data? So in this case, we were showing comparing different systems on like these open data sets. What I would recommend is that you'd want to take some comparisons like this, and then run the systems against your own data set and see what the distributions look like. For example, we saw that in the summary data set, we saw some of the distributions of the data. So like with SumAval, it was very skewed towards positive human judgments. So if you run your data set and the models that were predicting sort of like a more or less accurate scores for SumAval are predicting much lower for yours, that might be signs of a problem. So yeah, that's be sort of the advice is like you want to, when you pick the sort of the open data set that you think is a good test, is a good example for your data, get the distributions on that because we have labels, and then compare it to the distributions when it's run on yours. So this is sort of a challenging thing. So I'd say like you probably going to want to because the metric, this is the metric for either measuring the measurement system or your system. So let's start with the measuring the measurement system. That's going to be dependent on the labels in the data set. So, like as we saw in the summarization data set, some people were using a Spearman correlation, but that seemed kind of inappropriate, so we switched to an error one. And then when we went to the HalluBench one, they have a binary one, so like either Spearman correlation or error doesn't really work with error, so we sort of treated it like a classification issue, and we just calculated accuracy. Um, Again, if let's say we had all systems that were giving very high granularity answers, probably would have done like an area under the ROC curve instead of just accuracy. So it's going to be dependent on your data set for measuring the measurement system. Now, for measuring your own system, you're going to probably want to take a few different metrics. The primary one you want to look at for accuracy for like the actual hallucination detection. It's going to kind of depend on your system and what it outputs. So, for example, if you pick the Pythia system, you're going to want to that our accuracy metric, which is based off of the entailment and the contradiction. That one should give you a good idea of what's going on. You may want to actually weight it depending on your interest. If you are but if you're doing your system, there's other validators that you may also want to run. Like for example, in the Pythia system that you can sign up for, we have a whole set of other validators, and there may be things like you want to detect like the reading level. Maybe you even just want to monitor like the length of the data that you're outputting. So, for example, why you want to monitor these other metrics? If you are, let's say, producing summaries of medical documents for the patient, then you have highly technical language that needs to be put in less technical language. So you'd want to measure to make sure that your system is doing that. And as far as for length, your customers may be paying based off the length of the data that you produce, but if you're using any of these services like OpenAI, you will also be, if you're using their model, you'll also be paying, to some degree off the amount of tokens generated. So you want to keep track of that and make sure that your data is not like producing overly long or perhaps even overly short responses. Yeah. So if you don't have your own data, you can use one of these open data sets, and instead of using it to measure the measurement system, and where we're seeing how. So when we measure the measurement system, we take in these responses that are in the data set, and we see whether our measurements match what's in the data, right? But you could just provide your own output. So you could like take some of the stuff from HalluBench and run it through your own Q&A system, see what answers it provides, and then similar to one of the previous questions, you can look to see how the distribution of measurements on your provided answers look to the one in the system. So, for example, let's say we have one where like a lot of the ones in HalluBench, they're kind of like 50-50, they're pretty balanced. If you have your responses and you run it through, and then like you're getting like a much higher a rate of like high score, so it's like the measurement system thinks your application is very good. That's probably a good sign. That means that you probably do have a better set of responses than what came with the data set. And obviously, if it's much lower, that'd be the problem. Oh, it's not limited to a specific industry. So that's a great question. So, with Pythia, we've done stuff in in like with some clinical work. We've worked in some like generic sort of data sets and domains. Also done some work like on financial side. So there's nothing that limits it to an industry. I would say that I think like the future of this is building more specialization, especially in like models, but also in prompts. And for anything like RAG that uses like another data set, having specialized data sets that it requires. But For right now, like you can usually get started with like a more generic setup, and then begin tuning it to your problems, your use cases, your data. Yes, we do. Actually, I think we have a link to that. I think it should be available. Um, yeah, you can try it out, see how it works for your data. The previous webinar we did, Aline and I talked about this, and Aline walked through like how you set it up with your system. And yes, it's really easy to do. Uh, cool. So thank you everyone for attending this webinar, and stay tuned for our future developments.